Okay, we are going to do just a little bit of lecturing here, just to keep on pace, and then we will take a little break, and we will take the exam there. You know, somewhere around the start there of lab. Okay, so let us get going on this. So we've been talking about obviously bonding here in chapter 3. And last time we got into drawing Lewis structures and the proper sort of procedure to draw those guys. Remember, if you follow the procedure as we sort of talked about, you should end up with a pretty good structure that you need to draw. Really, the important parts are making sure that you got the correct number of valence electrons, making a single bond, and then continuing on to make one bond to everybody, and then add in your double bond electrons around the atoms on the outside first, and then any leftover electrons goes to the central atom in pairs. Remember that you do want to kind of save double bonding and triple bonding to sort of fix things. Again, if somebody does not meet the octet rule, that is where you want to basically kind of fix up that situation by making a double bond or triple bond. The result of double bonding or triple bonding means that we are not really adding more electrons, but we're actually bringing electrons in to sort of fix a problem. So if somebody is short, we can bring those electrons in, and we can basically get everybody to 8 electrons, except for hydrogen, obviously, that needs 2 without actually adding additional electrons. We also talked about, the idea of formal charge, and we could use formal charge to help us understand, whether or not one sort of Lewis structure is better than another. Remember, we could calculate formal charge by taking the number of valence electrons in the free element minus the number of non-bonding electrons minus half the number of bonding electrons. And basically what that will do to us is give us sort of the charge, if you will, of every element in that sort of arrangement in that compound. The best sort of situation is to sort of what referred to sometimes as minimizing the formal charge, which means that you could get to sort of a 0 formal charge overall. Usually very large sort of numbers of formal charges is not the best probably structure that you could draw. Also, if you have, again, that sort of similar distribution, we do want the more negative formal charge end up on the more electronegative atom within that sort of structure. Now we can use that to determine what sort of structure might be better than another. Again, because you could come up with obviously different ways of connecting everybody together with those elements that are present. And as we saw, I think with like formaldehyde, for example, we saw that the 2 hydrogens attached to the carbon works much better than 1 hydrogen attached to the carbon and a hydrogen attached to the oxygen in terms of formal charge. We also sort of finished up as last time talking about sort of bond enthalpy, which is probably the only very little bit of energy sort of talk and calculations that we do in this class. But remember that when we do break bonds, it's endothermic, and when we make bonds, it's exothermic. So when we're trying to figure out in terms of a reaction based on bond enthalpy or bond energy, we can basically add up all the bonds that we're breaking on the reactant side or the starting side of the reaction, and then basically add up all the energy required to make all the bonds on the product side, and basically take the difference. Again, the making being exothermic gets that negative sort of number. The endothermic, or the breaking part, is positive. So when we add those together, we get an overall value, obviously, for the energy of the reaction, or the delta H. And again, if that's positive or negative, will tell us whether or not overall, based on bond energy, was there sort of a net release of energy as a result of all these bonds being made and broken, or was there sort of a net absorption of energy as a result of breaking the bonds and making the bonds? And again, endothermic meaning you end up with a positive value for energy, exothermic meaning you end up with a negative value. Any questions on any of that stuff there that we sort of covered, I think, the last couple of times? All right, so we really did finish up, I think, talking about resonance structures. And remember, you can draw resonance structures, which are really just structures where you do have a couple of options as to, for example, where you can put that double bond. And you could draw an equivalent sort of structure by moving the double bond around to different locations like we saw in carbonate. And you can draw any one of the resonance structures, which are usually sort of indicated with those arrows in a situation. And they're all sort of equivalent. And that's because really those double bond electrons are moving around. They're delocalized, which means, again, at any given point in time, for example, in the carbonate one, as we talked about, it could be upward, it could be to the sides in terms of where the double bond is sort of located. So that's another sort of thing that we talked about. So where we left off on was, we talked a lot about sort of when we're drawing these things and the octet rule and sort of obeying the octet rule. But there is a lot of situations where sometimes the octet rule is really not obeyed. And there's kind of three major exceptions to the octet rule that we're going to talk about now in terms of ones that we will sometimes come across. And I'll talk about the ones that, we will see most often and probably the ones you might not see as much. The first type of exception is what is referred to as an incomplete octet. And an incomplete octet is pretty much what it sort of sounds like. In an incomplete octet, we basically have less than 8 valence electrons around it. And there are certain elements that are sort of perfectly fine and perfectly happy sort of in that situation. The two that we come across the most, and really the one that we come across the most, it would be boron. Boron, right there, kind of right where that staircase comes to the corner there above aluminum on the periodic table. It is perfectly fine with less than 8 electrons around it. Beryllium, to an extent, also kind of included in here. Although, beryllium is a metal, so, it can sort of behave a little bit like a non-metal, but it is kind of using that example. But boron is probably the one that you will see the most. And as you can see here, the boron on the bottom here, boron trifluoride has 2, 4, and 6 electrons around it. And it's really perfectly happy with it. Again, beryllium, aluminum, sometimes included in that group, although most cases what we come across would be something like boron, again, because it's kind of non-metal sharing of electrons sort of happening. So really boron sort of elements or compounds that contain boron can go less than 8, and it's perfectly okay in that situation. Another exception to the octet rule is one that's referred to as an odd number of electrons. And here's a couple of examples, NO and NO2. And again, when you do sort of the calculation for the valence electrons for NO, that's 5 and 6, which is 11 electrons. And obviously you have 1 unpaired electron. So in these situations, we end up with this 1 unpaired electron that's present. Same thing over here. We end up with this 1 unpaired electron that's present. And these are, sometimes what are referred to as radicals or free radicals. Those are things that have kind of 1 unpaired electron. Because of that 1 unpaired electron, they are very reactive, which means, they will continue to go on and react very, very quickly in a lot of situations because it's not really optimal, sort of that 1 electron situation, and it's trying to fix that problem. So we find these things very, very reactive. A lot of sort of atmospheric sort of chemistry involving chlorine involves sort of free radicals like that, and they're very, very reactive because of that sort of unpaired electron that it has present. Now, those two sort of exceptions to the octet rule, out of those two, again, maybe the incomplete octet with boron is the one that maybe you'll see the most. Occasionally, you'll see an odd number of electrons. But really the sort of exception to the octet rule, the third exception to the octet rule, is the one that we see pretty much the most in this particular class. And that is what is referred to as an expanded octet. And in an expanded octet, pretty much like the name implies, we are going above 8 electrons. So that is something that we see in a lot of situations in this class. In fact, there's a ton of geometries involving sort of expanded octet. So, the other ones, we come across occasionally, but, in this class and probably a lot of your situations, this expanded octet is the exception that we see a lot. So you see this sort of expanded octet and more than 8 electrons happening a lot, especially in this class and stuff like that. So what does that mean? Who has the ability to sort of do that? Well, if you look at the periodic table, there's sort of a location on the periodic table where we see situations where the expanded octet can definitely occur. And if we look on the periodic table, just going to draw a little periodic table action there. Right around, we got NOF and PSCl. And right there at sulfur, basically, so where we find sulfur on the periodic table, pretty much sulfur. And if you kind of go left and right a little bit and down, those guys have the ability to do the expanded octet. You may be wondering, why does right at sulfur have the ability to do that sort of expanded octet? And the reason for it has to do with some of the stuff that we talked about previously, and that is sulfur right here is in period 3 of the periodic table. Period 3 means that it is the n equals 3 level of the periodic table, and that is where we first start to see d orbitals available. So remember that d orbitals basically start on the 3rd energy level, and that is where we start to see it, which means although something like, for example, sulfur may not be actually using their d orbitals, they do have the d orbitals available to them basically to house those extra electrons. So because they have those d orbitals available to them to house those electrons, they're able to actually go over 8, and they're able to sort of go obviously upwards of 12 electrons around it is where we get to on those guys. That also means that if you talk about somebody like here, for example, in the period above it, in the 2nd period, those guys cannot go above 8. So these guys in the 2nd period, they definitely cannot go above 8. That is because on the 2nd energy level, they do not have the d orbitals available to them. So nitrogen, oxygen, carbon, those guys, they have to obey the octet rule no matter what the situation is. They don't have the ability actually to go above 8. But if you go to where sulfur is, kind of go to the right, to the left a little bit, and then down in sort of the non-metal region, those guys have definitely the ability to go above 8. And again, it is this sort of exception to the octet rule that you see a lot in this particular class and in most chemistry classes, is that sort of expanded octet. Any questions on that there? Okay, so let's take a look at an example. So they said SF6 was an example there. And if we look at an example of that and sort of draw the Lewis structure for SF6, we would follow the same sort of arrangement there. We got sulfur, which is group 6. We got, what we got there? We got fluorine, which is group 7, and there's 6 of them. That's a lot of math there. So that is 7 times 6 plus a 6. So we'll do the math there on the calculator since it's early. 48 electrons sounds like a winner. So we would arrange this such as this. We put obviously the sulfur in the middle. We would approach it kind of the same way. In this case, though, we just got a few or a couple more fluorines to sort of arrange around. We would apply the kind of the same approach, a single bond from the center atom to each of the outside atoms. We would again also follow the same approach and fill up the outside ones until everybody on the outside ones there had 8 electrons around it. And at that point, obviously, we would want to make sure that we have distributed all of our electrons. And at this point, we have. And obviously, everybody has met the octet rule, especially on the outside. And here we do see with our sulfur that we have 2, 4, 6, 8, 10, and 12 electrons around it. Again, it's perfectly okay with that. It has the ability to do that. It's okay in that situation. Any questions on that particular one there? So why is this important, or why do we see this? Again, we do see it because they do have the ability to do that. This also explains maybe why this, in combination with some other things that we talked about, why you may have, when you draw something like sulfate here. So if I draw sulfate, again, following the same sort of situation, we got 6 for our sulfur. We got 4 oxygens, which are also 6. We have our -2, which means we're going to add 2 to the total. That is 24, 26, and then 32, if I'm not mistaken, in terms of that. So if you follow sort of the same approach here, we'll take our sulfur, we got our oxygens. And this is one way in which you could draw sulfate. And kind of filling up everybody. This obviously meets the octet rule. All the oxygens have 8 around it. Sulfur also has 8. And that is a picture, right, that you could draw for sulfate. You may also have seen sulfate with some double bonds happening. And again, also has the ability to do this because sulfur can do that expanded octet. So sometimes, you know, if you Google the answer, which you should not do, but if in case you do, you might also see sulfate may be drawn such as this as well. Again, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32 electrons. Now, you may say which one is sort of the better structure. So because we do run into the situation, obviously, in this case, we have 2 structures, which technically are okay. We can use our formal charges we talked about earlier to decide, you know, which one might be the better structure of the 2 and why maybe you see one versus the other in certain situations. So why don't you take a moment and calculate the formal charge on all the elements in each of these, and then determine which one, based on formal charge, should be a better structure. So take a moment or two and see what you come up with. Let's take a look and see how we're doing. Grab something. So let's start with the structure on the left. So let's take a look at the formal charge that's going on with this guy. And we'll start with our oxygen there. So we'll do our single bonded oxygen like we've done before. Again, the formal charge here would be 6 minus 6 for the non-bonding electrons, minus 1/2 of our bonding, which is 2 for this guy right there. And that's going to give us a -1, 6 minus 6 minus 1, basically. That means all these oxygens are the same. So all these oxygens here in this structure are carrying a -1 charge. So let's take a look at the sulfur in the middle. So the sulfur in the middle has got 6 minus 0. Again, no dots on the sulfur. Minus 1/2 of 8 electrons. That's 6 minus 2 base. I'm sorry, 6 minus 4, which is 2 in this particular case. And that gives us a +2. So our sort of formal charge arrangement that we got going on here in our structure on the left is -1s at the oxygens. We have a +2 there on the central atom. So let's see what happens when we look over here at our sort of double bonded expanded octet here with the sulfur. Again, with our single bonded oxygen, we are going to obviously end up the same as what we did on the left there. That's going to be 6 minus 6 minus 1/2 of 2, going to give us a -1. So in this structure, much like the other structure, our single bonded oxygens are also going to carry that -1 charge. Here with our double bonded oxygen, we have 6 minus 4 for our non-bonding electrons, minus 1/2 of 4, and that's going to give us 0 here. So for both of those double bonded guys. Next, we will have our sulfur, which is a little bit different here. We got double bonds happening there, single sort of bonds happening there. That's going to give us 6 minus 0 minus 1/2 of 2, 4, 6, 8, 10, 12. And that's basically 6 minus 6, which is 0. So now upon comparison of these two structures here, and after looking and tying together what we talked about last time, which is formal charge, if we had to choose between these two, the structure here on the right is probably the better structure of the two, which is why you will very commonly see sort of sulfate double bonded here. Again, it minimizes the formal charge. Remember over here we had, 4 -1s. We're able to turn 2 of those into zeros, which minimizes those down to 0. Remember, 0 is sort of optimal. We also took this kind of relatively large formal charge we had on the sulfur, and by double bonding it, we were also able to minimize over there as well. So we definitely were able to minimize a lot of the formal charge that we get there in this particular case. And, if you had to sort of choose between the two structures based on formal charge, the structure on the right probably would be the better choice to choose from. If you weren't asked to make the decision based on formal charge and just asked to draw a Lewis structure, either one of these probably would be acceptable, but really based on formal charge, and probably a better structure is found on the right-hand side. And again, we could get to that structure because sulfur, being from period number 3, has that ability to, again, go above those 8 electrons and do the expanded octet. Any questions on that there? All right, so why don't you try just a couple here? Why don't we do, let's do BrCl5. So why don't you draw the Lewis structure for BrCl5? And why don't we do ClF3 and see what you come up with. So why don't you draw those two Lewis structures and see what you end up with. Start with the BrCl5. Again, we just want to approach these really the same way as the other sort of way that we talked about, sort of drawing these guys. So we do want to kind of figure out our total number of valence electrons. So bromine is obviously group 7, and there's 5 chlorines, which is also group 7. So that is 35, and 7 is 42 valence electrons. Again, we're going to arrange it logically. In this case, bromine and chlorine are really in the same group. Bromine is lower down, which means it's less electronegative. And again, same logical sort of thought process as we did before. There's really one bromine here, 5 chlorines. So I would say probably 98% of the time, or even 99% of the time, that one guy will be in the middle and pretty much everything else will be sort of directly attached to it. And in this case, you could place the 5th chlorine wherever you like, to the left, right, down, doesn't really matter. We're still going to do our same sort of make a single bond to the central atom from to everybody on the outside. That's 2, 4, 6, 8, 10 in that case, giving us 32 more electrons to go. Those are going to go on the outside. Again, we want to do them in pairs. We want to make sure that we kind of complete the octet for all the outside ones first. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and 30 at that point. And we want to see if we have used up all of our electrons, and I don't think we did because I stopped counting there, but we basically have 1, 2, 3, 4, 5 atoms that have 8 electrons. So 5 times 8 is 40, which means we still have 2 more electrons from our original 42 that we do need to place. So just like we did before, after we fill up everybody on the outside, which clearly we have at this point, those 2 electrons then go to the center atom. And again, they are placed on there as pairs, so lone pairs. So again, following the same procedure, single bonds, filling up all the outside ones with 8 electrons. Obviously, same rule applies. If you had a hydrogen on the outside, obviously, you would not obviously go more than 8 electrons. And just like previously, if we filled up everybody on the outside, but still have electrons to go, again, we do place them as pairs there on the central atom in that particular case. Any questions on that there? And that again should now be our correct structure. Everybody has 8. The chlorines have 8. Bromine, which if you look on the periodic table, again, is below sulfur, has the ability to do the expanded octet, which obviously it did in this case. So our bromine that doesn't have 8 has in this case 2, 4, 6, 8, 10, 12 electrons around it, which makes it perfectly fine in that situation. Any questions on that drawing there? All right. So again, following sort of the same approach here, we got chlorine, which is 7. We have 3 fluorines, which are also 7, which is 21, and that is 28 valence electrons. Same approach here. Again, chlorine obviously less electronegative than fluorine. Obviously here as well, chlorine's just 1, and you got 3 fluorines, so chlorine here in the middle, and our fluorine attached. And again, you could put the fluorine on the bottom. You could go up on top like I did here. Going to make our single bond. And we do get 2, 4, 6 electrons down there. And that means 22 to go, I think. So 2, 4, 6, 8, 10, 12, 14, 16, 18. At this point, everybody on the outside is full. At this point, though, I've only used 24 electrons, 8 around. I still have 4 more electrons to go from here. That means that just like we did over here, those electrons then would go to the central atom. And again, we're going to put them on as pairs. In this case, actually 2 pairs of non-bonding electrons end up there. That gives us our grand total 28 around, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. We have now placed all of our electrons. All the fluorines are good. They have 8. And our chlorine, 2, 4, 6, 8, 10 electrons. Again, it's perfectly okay because our chlorine is right next door to our sulfur, which is on group number 3, or period number 3, and it's able to go with that expanded octet. Any questions on sort of expanded octets and how to draw those? Again, like I said, out of those 3, you obviously do need to be familiar with all 3 of those exceptions to the octet rule, and that is, again, our odd number of electrons, which we really honestly don't come across very much here. Our incomplete octet, which does come across occasionally. But again, out of those 3, the one that we see the most, and we'll see with geometry and stuff like that, is the one we're talking about here in a little bit more detail, which is our expanded octet. We see that a lot. So after beating into your head, probably don't go over 8, don't go over 8. We'll kind of go over 8 a lot in this particular class. So that exception, we see a lot going on here. Any questions on any of those things? Now, as we just saw there with the sort of the sulfate example, even with the expanded octet and so forth, if you still follow sort of the rules we talked about in terms of drawing sort of Lewis structures, you will end up with probably a fairly good picture. Is it always going to give you maybe the best picture? So as we saw there with sulfate, not necessarily. But again, that's where we could kind of tie our formal charge into it if we were really looking to try to kind of pick the best picture. So remember, you don't have to worry about all the different combinations or sort of using formal charge to pick the better Lewis structure, unless obviously asked to do so. Otherwise, again, you could just follow those sort of rules for drawing it in, maybe 8, 9 times out of 10, you should probably end up with a pretty good picture or Lewis structure. Any questions on any of that there? All right, so that actually completes chapter 3. It really doesn't, but it completes the part of chapter 3 we're going to talk about right now. There's one more section of chapter 3, which we're going to go back to after the next chapter, and that is about nomenclature and naming. So we'll talk about all that naming stuff. We'll come back to chapter 3, but for the bonding and all that, that pretty much is chapter 3 at this point. Where we're going to go next is to chapter 4, which is about geometry and molecular geometry, electron pair geometry. We'll also talk about hybridization and some other bonding sort of models that happen there in chapter 4. But I think since we do have an exam, and I promise it wouldn't be a super long lecture, which obviously it won't be right now, we will lay it up there, I think, for today. And that way we won't stop in the middle of the geometry and all that kind of stuff.